Attendees are in listen-only mode.
Good morning, everybody, and welcome to today's webinar. Also, good afternoon to our folks that are coming in from Europe. Thank you for attending, even though this is probably your evening time. We do appreciate it. Today, we're going to talk about ground bond and ground continuity testing. We've been doing HiPot testing over the course of the last couple presentations, and now we want to try to delve into another facet of electrical safety testing. Before we get started, I do have some notes on the webinar. There's a couple utilities you have at your disposal. You'll notice on the bar on the right-hand side, which is your control panel for the GoToMeeting. There are two main utilities that you're going to use. There is a chat utility and there is a Q&A utility. If you have any questions related to the meeting itself, as in you can't see a slide or my audio cuts out or anything like that, please address those questions, inquiries, concerns to Jim Kennedy through the chat line, and he'll be able to help you out there. If you have any questions regarding the material itself, please address those to Syed Abidi. Syed is helping us today. He's our applications engineer. He's very knowledgeable in this field, which is why he's the guy handling our questions today, and address those his way. This webinar is being recorded and will be available to view usually within a day or so on our website. We'll have it up. You can look, if you go to support materials, webinars, you'll see a webinar archive. And we keep, I believe, ones from the last entire year, or even more, actually. We might have about 14, 15 up there, and we usually do about one a month. If you do want a copy of the slides in the presentation itself, contact Jim Kennedy, email him, jimk@asresearch.com, and he can send you over a copy of those. We like to freely pass these out. They're great training resources, and that's why we do these webinars for free, because obviously safety starts with education, and we want you guys not only to know how all these tests work, how our equipment works, but also to keep yourself safe. So that being said, let us move forward. Just a quick recap of the previous webinar. Our previous webinar was HiPot Testing 102. As you might imagine, the one before that was HiPot Testing 101. What we discussed last time, should you have an interest to look it up on our website, was some basics, I guess, on HiPot testing. 101 was the real basics, and Syed performed that one a couple months ago. I did the one last month, which was 102. We talked about leakage current limits for your HiPot test, determining those limits. We delved into a bit of 500 VA testing, which is your higher leakage current HiPot testing, and why it's necessary. And that kind of plays into the whole line load regulation of your HiPot tester. Can it maintain the voltage output? And if it can't, why you need more energy in order to successfully perform a HiPot test. We also went into fault detection. The fault detection was more specific to our instruments, since that's pretty much our basis for comparison here, but how our fault detectors work, what they're doing, what are the various fault detectors, and how they can help you in the lab or production line. And then we just went over some extra features of our HiPot testers. And today, we are going to delve into a bit of a different topic. This is something that if you're doing HiPot testing, you are most likely doing these tests as well. I'd say probably about 90% of you, depending on the type of product you're manufacturing. But we want to talk about ground bond, also called protective bonding or protective impedance testing, and ground continuity. And the reason that I think it's important to put both of these terms in the title is because standards tend to use these terms interchangeably. But they can, when we refer to them, we do mean two very different things, and that's really what I want to point out here. So we're going to stick to one set terminology, but as I go through the descriptions and the examples, you will probably be able to relate that to your standard and say, oh yeah, he's talking about protective impedance testing, or he's just talking about a quick routine bond or continuity check. So there is a difference there, and that's why you'll see in my breakout here, we're first going to talk about ground. Obviously, if we want to understand bonding and continuity testing, it's pretty important to understand what a ground is, as well as the types of products that you run these tests on. And then we're going to kind of break out and get a little more specific. We'll begin after that by talking about the bonding test. What is it? What do the standards say about it? And then looking at some test examples. Same with ground continuity. What is it? What do the standards have to say about it? And then I have some videos to show you guys, just real quick, short videos that give you an example of a bonding test, that give you an example of a continuity test. And then finally, we're going to kind of compare and contrast these two tests to really understand the difference between the two, because we've been able to change people's minds in the past that might have been running one of these tests over the other and asking us, hey, which one of these should I really run? And obviously you have to take that on a case-by-case basis, but we can certainly give our suggestions and say, in all honesty, we think you should be running this test. So we want to compare the two, show you why they're different, and then I have another video that kind of demonstrates this point as well. I'm hoping this webinar will go about 45 minutes. Might be a little bit shorter depending on how quickly I move through the material. I know we have the webinar slated for an hour. I never like to take the full hour because I like to leave it open at the end for some questions. And I also like to keep people's attention. And I feel sometimes some things beyond 40, 45 minutes, people tend to drift, which is why I like to include lots of videos. We're also doing something different in this particular webinar, if you've attended some of our other ones, is we give audience polls. So we have 2 polls in the webinar. We're going to ask you some questions, and unlike what we've done in the other webinars, we are going to discuss those poll results. In the past, we've seen that the results we get from the polls are rather interesting, and we've shared that information amongst ourselves, but we do feel that these answers would benefit you, the audience, as well. So today we do want to discuss those a little bit. So let's start out with a poll. What we're going to ask you guys is ground bond versus ground continuity. Take a look at the poll question. I'm going to give you guys about 60 seconds to go ahead and answer this question, and then we will talk about the results.
Hey Nick, so we asked, are you performing ground bond or ground continuity testing?
Yep.
So 49% are performing ground bond, and 30% are performing continuity, and 21% are neither. And we had about 91% vote. So pretty good participation.
Yeah, that is good participation, and thank you everybody for participating in these polls. Not only is this useful information for us, but it's also useful information for our customers, because we get a feel for what you guys are doing and how we can best help fit you into a unit that might work, or even just give you general information. So that's a really interesting split. That's, I guess, kind of about what I expected. I do see the continuity test more than the bonding test, and I do apologize, we really didn't explain the difference between the two fully. So I'm hoping that there was an understanding there. It seems that there is a base understanding of what I'm talking about. I think most people know bond versus continuity, the general concepts behind each and what their difference is, and that some people weren't testing them at all, which makes sense with certain products, and we're going to get into that in a minute. So that is some interesting results. Thank you, Jim. So moving on, before we get into bonding and continuity, what's a ground? You know, this is one of those terms that even if you went to engineering school and somebody said, hey, what's a ground? You might have to pause for a second and think, yeah, what is a ground? Because there's a lot of different concepts that get thrown around for earth or ground. In some cases, earth might not even necessarily mean ground. But when we're talking about it here, ground or earth can have numerous functions and meanings. But the main purpose of the ground for what we're talking about in this webinar is to reduce the risk of electrical shock. It's essentially a reference point for an electrical circuit. As most of the people who are listening know, when you apply a voltage, voltage is a force. So it's being applied from point A to point B, let's just say. Or in terms of an electrical circuit, you have your source sourcing the voltage, and it's going to drop down to your reference point, and then of course the current comes back and returns to the source. So for example, if you start the blender in your house, you have 120 volts dropping across that circuit. A drop implies that there's a reference point. The ground is what we're talking about as a reference point. Now, your reference point might not necessarily be ground, but ground is always a reference point, and I think that's an important distinction to make. So when somebody asks what is ground or earth, I simply say it's your 0-volt reference point. That's my favorite way to think about it. And if you do have a good solid ground, it should be a 0-volt reference point. You shouldn't have a floating circuit, although, you know, in certain cases it's necessary. We're not going to get into all that, but let's just think about it as your 0-volt reference point. It gives a good reference point for all of your circuits, and that's important, especially when we're talking about safety. And then this goes into the point of a common return path for your electrical circuit. This also plays into modern power distribution when I'm talking about safety and things of this nature. So just a really, really basic diagram here. You can see on the left-hand side here, when we're talking about modern power distribution, we have our sourcing, and I tried to show that through some transmission lines right there, and obviously that voltage is going to get stepped down via a distribution station, and then from there it's going to go out to neighborhoods and homes and businesses and all that good stuff. So, you know, I just represented a capacitance in parallel with the resistance as kind of the load. Obviously it's a lot more complex than that, but we can break it down in these terms. So you see on the left-hand side there, everything's flowing smooth. The light bulbs in the guy's house are on. Everything's working normally. On the right-hand side, what we're assuming there is that we have an insulation fault. Let's just say insulation goes bad in a home or something along those lines. It happens all the time, you know, especially older homes, your insulation goes. You have a fault, and let's say your line has now shorted directly to, let's just say a metal fixture in your house. That can be really bad news because your line is now shorted to a metal fixture. Metal's conductive. What if you go up and you touch that fixture, and the electricity sees you as a pretty nice looking path in which to go? And let's just say that you're barefoot or you're grounded. If you're grounded and it's the only path available, guess where that electricity is going? It's going right through you, and that's going to spell a bad day for you. With the ground in place, as you can see here, basically what we're showing is that instead of going through you, we are providing another path, a more attractive path for the electricity to go. Because remember, electricity is a lazy beast. It's going to take the path of least resistance. And if you make that path of least resistance very basically saying, hey, look, this path is going to be a lot better for you than this guy over here, it's going to follow it. So what we're showing in that diagram there is an insulation fault, a shorting to the case, and now all that fault current is flowing to ground instead of through a person and potentially killing somebody with an electrical shock. So I want to mention there's a couple different types of term for ground here that we can refer to. We have a system or service ground, and what I most commonly refer to as an equipment ground. So system or service ground, it's basically one conductor, commonly referred to as the neutral, and the neutral is generally grounded. And this conductor is grounded at the generator, the transformer, again at the service entrance of a building. And basically what this is designed to do is protect machines, tools, and insulate against damage with this system or service ground. Now there's a little bit of a difference here when we're talking about an equipment ground. This basically provides an additional ground conductor and products to safeguard the operator against electrical shocks should the insulation of the product fail. So there's a distinguishing factor here. Service ground, you think, protect buildings, tools, insulation. So basically protect things against damage, whereas equipment ground is designed to protect operators or users, basically you and me, against electrical shock hazards. And that's really what the purpose of this webinar is. We're mostly going to be talking about it in terms of equipment grounds. You can certainly consider service grounds here. It's a test, a ground bond and the continuity test is certainly something that can be used to show continuity of a service ground, but what I'm referring to here is electrical shock hazards. What we want to do with equipment and service stations as well, you want to tie all of your metal chassis points, anything that's accessible to somebody, all tie them to ground. So why would you want to tie all these points to ground? Well, what you're doing essentially is you're putting all these points at the same potential. And that's very important because as we saw on the previous slide, it gives you a reference point. And a reference point is important. Let's just say that we ground one piece of equipment solidly to 0 volts, and then there's another piece of equipment right next to it which isn't solidly grounded. What can happen, and again, this is a very basic example, but that metal chassis points on that product, let's just say it's not grounded very well, what if that hovers around 4 or 5 volts rather than 0 volts? But on the other one, on the other piece of equipment, it's at 0 volts. You have a 5-volt potential difference now between those 2 points. So if you have contact between those 2 points, current can flow. Leakage current, fault current, whatever you want to call it, it can flow. And it might be able to flow through a person. So that's why it's very important. You want to reference everything at the same point because it's going to keep you safe and not cause what we call current loops or ground loops where you have various points at different potentials. Because remember, if you have different potentials at different points, current can flow. Giving it an impedance or a resistance between those points, it's going to cause current to flow. It's the bottom line here. And this kind of plays into electrical products as well. So again, when we're talking about equipment ground, these are the type of plugs that you'll usually see on a piece of equipment. And when I'm talking class 1, class 2 here, I'm talking about grounding and insulation. There's all types of class references for all different things. We're talking about class insulation here. So electrical products can be classified according to their insulation type. So on a class 1 product, I'm sure everybody in this room has seen both of these. It terminates in a 3-prong line cord. You see the 2 blades at the top? Those are your 2 standard blades. Those are your line and neutral, so your current carrying conductors. And then you got that little guy on the bottom, usually it's round, and that is your ground. And the ground prong should connect solidly to the product chassis. Remember, we were talking about those accessible points. That's what I mean. So basically what you have here is you have safety through a level of basic insulation and proper grounding. So something that's important to remember here when we're talking about insulation and grounding and all that good stuff is essentially what we're always looking for is 2 levels of protection for operator safety. We want 2 levels of protection. So in a class 1 product, those 2 levels are the basic insulation and the grounding. Because should the insulation fail, you need a second line of defense, and that second line of defense is a low impedance path to ground so that the current flows down that way. But you also have what are called class 2 products, or double insulated products. They terminate in a 2-prong line cord, just line and neutral. So you might say to yourself, well, that's not grounded, isn't that dangerous? No, because what they do is you have protection through a double layer of insulation. So instead of just basic insulation, you also have double or reinforced insulation to make sure that should even one layer fail, you still have that second layer to protect the user. Again, a second level of protection. So this is something to keep in mind. And I'm wondering, as we were discussing about the poll before, we have people who are saying, well, we don't really perform these tests. I forgot what percentage it was, but it was, I think Jim said something along the lines of maybe 20%. Don't perform either of these tests. Well, if you have a class 2 product, that would actually make sense. You don't really need to perform a test like that because you don't have a ground path to check. You don't have a ground path to check for continuity or make sure it can handle fault current. What you have is a double layer of insulation. So most likely what you're doing for testing there instead is doing a higher voltage dielectric withstander HIPOT test to make sure that both layers of insulation can handle the electrical force necessary to keep the user safe. So basically the takeaway here is that Class 1 products provide electrical protection by employing basic insulation and a grounded chassis. Class 2 products use this reinforced or double layer of insulation. Now, when we're talking about rules and regulations here, you can't ignore the National Electrical Code, which is based off of NFPA 70, NFPA being the National Fire Protection Agency, and it stipulates the NEC, which is adopted in all 50 U.S. states. And the NEC itself gives requirements for grounding products and installation, and they also define what is a quote-unquote good ground. So it's nice because they do say, look, this is what you want to look for when you're looking for a solid ground. Obviously, the term good is very relative, so we need to further define that. So the National Electrical Code, as I mentioned before, is based off of NFPA 70. You can look up all that information online, and you can find these NEC codes online too. And it protects people and property from electrical hazards. That's basically what the goal here, the overarching goal of the National Electrical Code is. So if we bore down a little bit more to NEC 250-45, here's what they say. They say any exposed non-current carrying metal parts of a cord and plug connected equipment which may become energized shall be grounded. This just plays right off the concepts I was talking about in the previous few slides. It makes sense when you think about it in that respect. And if you drill down even a little bit further and get a little more specific, they define in 250-51 a good ground shall, number one, be permanent and continuous, which makes sense. We want a good solid path. Secondly, the capacity to conduct fault current. This is important. You need to have the capacity to conduct any fault current that's likely to be imposed upon a circuit. Because if you can't, all that's going to happen is the circuit's going to burn out, and now you have no ground, and once again, now you have a hazardous situation. Because if you've run into a situation where your insulation has already failed, and now your ground fails, there is no level of protection from shock hazard. And then finally, a low impedance path to ground that will limit the voltage. Or you could just say you need a low impedance path to ground. So basically, hey, it's got to be a set path, it's got to be heavy duty enough to conduct this fault current, and it's got to be really low impedance so that it looks very attractive for that electricity to follow. And I want you to keep these in mind as we run through talking about ground bond and ground continuity tests, because you're going to see why the ground bond test, in my opinion, is a much better test than the ground continuity test, and it's based, in my mind, off of this NEC 250-51 definition of what stipulates or constitutes a good ground. So before we get into that, we are going to talk about standards in a little bit, because obviously standards dictate how you're performing these tests and what tests you need to perform. So we are curious about standards you guys are testing to. So we have a quick poll here, and then we'll briefly talk about it.
Okay, Nick, we had about 75% of the attendees vote, and overwhelmingly it was 39% other. Of the ones that we listed, 19% are performing 60601-1 third edition. 19% are also performing or adhering to 61010-1 third edition, and then 60950-1 had 16%, and then 60335-1 rounded it up with 7%.
Okay, great. Good information there, and a lot on the other category, which is I find very interesting. For any of you who'd be interested to discuss your standard further, we're certainly curious what standard you're testing to. feel free to shoot us an email, info@asresearch.com, and say, hey, look, I attended the webinar. I was one of the guys who was in the other category, and this is the standard we're testing to. We do have a copy of many standards, and we're always open to discuss your requirements, what you guys are doing, what we recommend, and obviously equipment that can go along with that. But we always like to chat about this stuff. We see it as fun. But it looked like there was almost a pretty even spread between 60601, 61010, and 60950. And for you guys who don't know, 60601, like Jim mentioned, is medical. 61010 is laboratory, equipment for laboratory use. And 60950 is IT and other related IT-type equipment. And those are three of what I call the Big Daddy standards that cover a very large portion of different types of products. So I'm not surprised that those were pretty well evenly matched. I almost would have thought 60335 would have had a few more attendees or a few more people testing the 60335 for household appliances, but it looked like it was a little bit reduced. So very interesting results, and it's important, the standards are important to mention here because, as I'm going to show you in a little bit, each standard, they dictate different ways that you need to do this and which tests you need to perform, and more importantly, where and when you need to perform them. So it's important to understand that there are some variations here depending on the standards we're dealing with. So, ground bonding, ground continuity tests. Let's give a quick overview here before we get into the nitty-gritty. Purpose. What is the purpose? Well, we've been talking about ground a lot, so you guys probably pretty much get what the purpose is. Ground bond and ground continuity tests are designed to check the ground connection on a product or a system, and it's how you ensure you have proper grounding. So your method here is to apply current to a ground point, a product, or a system, and you measure the potential drop across the ground circuit and calculate the circuit resistance. So you're applying this current, you know you're measuring this potential drop, and as a result of that you can get a resistance value to see, in fact, how low is the impedance on your grounding circuit. Is it low enough, and is there something you need to do to make a better or more attractive path for the electricity? Now, one important point I want to note here, because this is something that I refer to quite a bit, and I want to make sure that we have our terminology straight for the testing aspect. The ground bond tests are generally, and I say generally because it's not always, type tests. When I say type test, I mean your laboratory prototype testing. It's usually done on a sample basis per the standards and not on 100% routine testing. On the other hand, ground continuity tests are generally production line tests. So they're usually done on 100% of product that go up, just like the HiPot test. HiPot tests are your 100% production line, routine production line tests. Generally, continuity falls into that category as well. So the takeaway here is that these two types of tests are used to prove and verify that there is a low impedance path to ground for electrical products and systems, and that it ensures proper grounding. But again, there's a difference, and I think it's really important to highlight that difference. Now, let's get into the ground bond test. What do we got going on here? What I'm showing you here, this is just an image of our 8204 Omnia tester, which does HiPot, insulation resistance, continuity, and ground bond. And we're plugging in a product here. So what you see there is you have a return terminal, that's the little black cord on the bottom, that's connecting to the chassis of the product. We want to return on that so we can measure resistance. And then you see we have what's called the universal style adapter box there that we're plugging the fan into. And then the other portion of that is connected to, you see the red terminals there. The red terminals are the current terminals. So that's where high current is going to be generated. You'll also notice there's another little cord that's going to a little white terminal on top. That white terminal is the high voltage terminal. This particular setup would be designed for a ground bond and HiPot test to be run simultaneously, not simultaneously, sequentially. And in this case, we don't care about the HiPot connection, but as you can see, it's there. So what's going to happen is you're going to get current generated from that red terminal. It's going to go through to the adapter box. The current is injected on the ground pin, and then it's looking for the return path on the chassis point of the instrument. So electrically, what we have going on is this. On the left-hand side there, you can see our current transformer. You can see the current is injected onto the cord, which is right in the middle there. You see where it says line. That's represents a 3-prong cord, and that goes out to the DUT, which you can see represented as a resistance on the right-hand side, just a little box with some resistors in there. And you'll see we represented the path. You see the little ground, on the left-hand side, it's connected to the ground pin of the plug, and that goes through a low impedance path. And you'll see we have our return and our Kelvin connection returning back to the instrument. And I mentioned Kelvin because our units, if I step back here real quick, you'll notice that for the current and the return point, there's actually 4 ports. One's a current port, one's a return port, but the 2 little guys on top are sense plus and sense minus. What those do is those measure the voltage drop up to the point of application. So it essentially negates lead resistance automatically. That's what we call a Kelvin connection. So anyways, this is what's going on. So what's happening here is, let's just say we have a pass condition. You see we have current injected onto the ground pin. It goes through that low impedance path to ground. And all is well with the world because it can handle the current, and we have a low enough impedance that our unit says, hey, this circuit's a pass. On the flip side of that, you could run into a situation where it is not a pass. Either there is no ground circuit, or you have exceeded a limit for your ohmic measurement. And the unit said, hey, you said that you wanted a 150 milliohm high limit on this ground bond test. We measured 200 milliohms. This is a fail. So we don't have a continuous enough path. Either it's not continuous or it's not a low impedance enough to be considered a solid ground per whatever standard you might be testing to. So as you can see here, we did some circuits with the high pot test in the last webinar. This is even more simplistic than a high pot test. You're literally just measuring the resistance of a wire by applying high current. So I kept mentioning standards, and we talked about standards during the poll, so let's see what the standards have to say about this. Let's look at 60601 3rd edition. I'm glad I picked this one prior to the webinar because it actually fit in quite well with some of the poll results. So in any event, section 8.6.4 of this standard has the impedance and current carrying capability, what we refer to as the AC ground bond test. And we call it bond because bond simply basically refers to higher current. When we say bond, we mean we're applying AC high current to the circuit. Here's what the standard says. You need a current of 25 amps or 1.5 times the highest rated current. Of course, whichever is greater, plus or minus about 10%, is passed through this protective earthing circuit. That's the same circuit I just showed you in the previous slide. Same thing we're dealing with here. You apply it at a frequency of 50 or 60 hertz. I'm sure whatever your product is rated for, so rated frequency. And your no-load voltage drop across that circuit is not to exceed 6 volts. The pass criteria for this test is that the impedance of the protective earthing circuit on the DUT be less than or equal to 100 milliohms. But for DUTs with a non-detachable supply cord, it's 200 milliohms. As you would imagine there, if you have a detachable supply cord, you're going to measure that at the little ground pin on your product. If you add a cord and you can't remove it, obviously that's going to add some resistance. So they put a little leeway in the standard to be able to do that. Oftentimes, even if you are doing a ground bond test with a detachable piece of equipment, you'll still plug a cord in. But what you can do on a lot of modern-day ground bond testers is you can offset that resistance pretty easily so that it doesn't factor into your result, especially if you're kind of on the ragged edge of passing that test. Let's look at another standard, and the reason I like to show multiple standards here is I like to give you guys a feel for things outside your industry. What are the other standards saying? Are they similar? Do they have similar requirements between the various standards on tests like this? Section 17.2 of UL 1598, this is for luminaires, or luminaries, however you want to say that. Lighting stuff is what I like to say. Just say lighting stuff. You get a test current of 30 amps passed between the earth contact point and the accessible conductive part. So in this case, it's a little bit of a higher current, unless, of course, if you have a medical device that runs beyond 16 amps, then it's going to be higher than 25. Or 15 amps, it's going to be higher than 30. And your no-load voltage is 12 volts AC or DC. So I'm guessing depending on what type of product you're testing, you might have an AC or DC ground bond test. And your test time is 60 to 120 seconds. And I have a reference to clause 17.2.4 because there is a variation in the test time depending on what you're dealing with here. And the pass criteria is that the protective earthing circuit on the DUT be less than 100 milliohms. So actually that 100 milliohm number is pretty common throughout various standards. That seems to be a benchmark for equipment for the resistance of the ground circuit. And another common parameter that you're going to see on a lot of ground bond tests is the 120-second test. What that's for, that stems from the rating of many time-delayed fuses in building installations and things of that nature. They're designed to withstand fault current for a 2-minute time period. So they're having you apply this for a 2-minute time period on your product because even if your installation fails and you have fault current on your grounding circuit, it might stay there for a period of 2 minutes before that fuse blows or that circuit breaks to where it cuts it off to your product. So they want you to be able to stress that for a long enough period of time to prove that your ground circuit's going to be able to handle that fault current for the necessary period of time. In the medical device standard, I don't believe they actually give a time. I think they just say that a time necessary enough to obtain a meaningful reading, which, you know, maybe you don't need a full 120 seconds, but with the ground bond test, since you're dealing most of the time with an AC current and you're loading down the circuit with high amperage, I usually run it for at least 5 to 10 seconds just to make sure that it can handle it for a specific period of time. Sometimes really 1 second isn't enough time. You want that circuit to heat up because obviously as you heat up the grounding circuit, you're going to get a higher resistance, and you want your worst case scenario here to make sure your product's safe. Let's look at one more standard, the 60335 5th edition for household appliances. They say, very similar to the medical device standard, they say 25 amps or 1.5 times highest rated current, whichever is greater, which I believe is the exact language of the medical device standard, aside from the plus or minus 10% deal. Their no-load voltage is a little looser. They say 12 volts AC or DC instead of the 6 volts of the medical device standard, but the benchmark's the same. Again, you see this 100 milliohm number. Now, something to keep in mind, all these standards I've just shown you, these are all for the type testing aspect of the standard. These aren't routine production line tests, and we are going to talk about that in a couple minutes, actually. So before we do that, I wanted to show you guys an example of a ground bond test. So what I have here is, hopefully this works as well as it did when I was practicing this. I have a hyperlink to one of our YouTube videos that shows you how to use one of our ground bond testers. Something to keep in mind, we do have these available directly on our website and on our AR YouTube page. We have a series of quick start videos that show you how to use our equipment. This is one of them. It's a 4-minute, 23-second video, but I'm going to skip ahead to about the 2-minute mark because that's really what I want you guys to see. So, yes, let's see. So let's skip ahead to about 1 minute and 49 seconds. Just real quick here, guys, just so I can verify, could you guys hear the audio on this video? Can you hear that? You could. Okay, good. All right, so glad you guys got to see that quick video clip. As you saw, what we did there is I was just showing you guys how you can run a ground bond test, and as you can see, it's really simple. You just connect your 2 points and it pumps in the current. It's taking the voltage measurement automatically and showing you the resistance value. In that case, I believe it was about 39 milliohms right about, which is what I expected from that circuit. And you also saw I performed an offset on that unit as well. Most ground bond testers out there these days, ours and competitive units, they have offset features. They realize that, hey, sometimes you have long leads that lead up to your if you're on a production line where you have long spacing, a lot of cables, you might need to offset those numbers. So you can certainly do that and then run your test. So that was an example of a ground bond test. As you could see there, we were also using an enclosure for safety to make sure that nobody could come in contact with the energized circuit while it was testing. That was my uncut fingernail and extremely white arms you were able to see in that video. And you're going to be able to see it in the next video too when we talk about ground continuity testing. So when we talk about ground continuity testing, what we mean is a DC low current test to check circuit resistance. It's a similar concept to a ground bond test because you are applying current, it's taking a look at the voltage drop, and you get a resistance number. However, when I say DC low current, on our units, a DC continuity test, it's like 0.1 amps DC. So it's really, really low value. And sometimes for a continuity test, I'm not talking about our units in particular, but a lot of different ways to check continuity out there. You might have something like a light buzzer or battery buzzer combo thing. You might have seen these things where you have like a little pen with a light on it and it's got a clip, and you would put the clip on the chassis, much like I put that black lead on the chassis of the product in the video, and then you take the little pen and you'd apply it to your ground pin or another grounding point, and if the light goes on, it's telling you, hey, you have continuity. The problem that I have with this is that not all readings display an ohmic value. So while the light is going on, what value is it telling you? That could be up to 7 or 8 ohms. And when we're talking about a ground circuit, that's actually pretty high. So the continuity test is the same concept as a bonding test. You're simply checking for a continuous path on a ground circuit. However, there are some key differences between these two tests. Before we talk about those key differences, however, I want to show you a really quick example of running a continuity test on one of our bare bones units, the HiPot 3, which has built-in continuity features. So let's see this video come up here. I'm going to expand this, and I'm going to skip ahead since we're not too interested in learning about HiPot testing in this particular section. I'm going to skip ahead to about 4 minutes, 24 seconds. So again, this is our HiPot 3 instrument. So Saya just informed me that the audio was a little spotty on that video. Basically what I was showing here is that this is a HiPot tester, but it has a built-in continuity check function. We did that mostly because HiPot and continuity tests are usually run on most production lines, so it made sense to fit it in there. What I'm showing you here is you saw I plugged in a continuity check lead, and what that is looking for is continuity between the cont check and the return port. So again, you would apply the cont check lead to the ground pin and the return on the chassis, and as you can see, the light went on green. Now, fortunately on our units, you can set a high limit value for resistance. It goes up to about 1.5 ohms. But again, as long as it's under the 1.5 ohms, the light's going to go on. You can actually adjust that high limit too. You can set it to half an ohm if you wanted to. But again, you don't know the exact reading. It's just letting you know, hey, continuity is here. So if that's all you need to do, great. But there are some key differences here between the continuity and the bond test, and that's what we're going to talk about next. And I think that little green light lighting up and what I just mentioned is a really good segue into this. Before we get into the key differences, let's look at a couple standards here. So here's for IEC UL 61010-1 3rd edition. This is for laboratory type equipment, and Annex F contains the routine production line tests. So as you can see on the right-hand side, yes, you have a high pot test for routine production line, but more importantly on the left you have the continuity test. A continuity test to be run on protective earthing circuits. No current value specified. Simple continuity test to show the existence of a protective earthing circuit. So that test I just ran where the little green light goes on, that would be acceptable per this standard on a production line. However, not all standards treat continuity and bonding in the same sense. 60335 for household appliances. Remember, we saw the type test earlier in this webinar. Now here you see they don't have routine continuity. They have routine ground bond. So they have a test current of 10 amps, and I would consider 10 amps to be a bonding test. You have your no load voltage, and you have your same impedance like you have for a ground bond test, less than 200 milliohms for cord connected equipment, and for all other appliances, less than or equal to 100 milliohms. This is a key difference. There are many standards that call for routine, what we call bonding tests, and they basically say, hey, look, this continuity test isn't good enough, and let's talk about why that is. So finally we get into the ground bond versus the ground continuity test. So let's compare and contrast here for a second. The ground continuity test verifies the existence of a ground connection. Your little light, your battery buzzer, a little ohmic reading, whatever. It's going to tell you the path is there. That's great. And your reading in this one is generally given in ohms. You could have a 1 ohm, 2 ohm, 3 ohm, whatever the case might be. It's quick, it's easy to set up, it's easy to perform, which is why it's so popular on production lines. Obviously on a production line, time equates to money. You want to get this done as quickly as possible. And it's usually used as an extra feature during the high pot test, as you saw in that previous video. The bond test, similar concept, but instead of just verifying the existence of a ground connection, it verifies the integrity of the ground circuit because you're loading it down. As a result of you loading it down, not only are you saying, hey, this path exists, but it can handle this fault current too, which in my mind, why it's a much better test, because it's a much more stringent test than a ground continuity test. Your readings for a ground bond test are generally given in milliohms, and to me, it provides more valuable safety information about the DUT. It can also be combined with a high pot test for a more complete safety testing system. Actually, on our Omnia units, our Omnia 2 series, we have a feature called Dual Check, which will simultaneously run your ground bond, not continuity, it will simultaneously run your ground bond and high pot tests. So if you want to save some time on that production line, and you guys have an Omnia 2 or are interested in an Omnia 2, keep in mind that it can combine those two tests into one test. So when people come and ask me, which test do you recommend, I say, Mr. Customer, obviously this depends on your product. I don't know how you've type tested it, and I don't know what type of risk analysis you've gone through. But were I somebody going through a risk analysis on a product and I wanted to be extra careful about how I let these things out into the world, I usually recommend the bonding test. Maybe you don't have to go the full-blown 20, like say your type testing says 25 amps. Okay, great. And then for the routine testing in your standard, as we saw with 61010, it says, hey, no current is specified, just show that the path is there. Maybe you do a 5 or 10 amp test. You're still loading it down. You're still verifying the integrity. You're just not going full-bore type testing. That's also acceptable. Obviously, you want to check with your safety agencies, but I can tell you for that particular standard, even though the routine aspect tells you to do 25 amps or 40 amps or 2 times rated current, the production aspect says no current specified, you can get away with something else. Now, let's give an example here, and I think the table of the two differences between these two tests perfectly shows this. We have a 64-strand wire with all but one strand connected. Who knows what happened? Maybe somewhere in the production process something went awry and it got cut. Now let's just assume here, we show a cutaway, but let's just assume the insulation is still over this wire. So you wouldn't be able to see this. We at the webinar can see this, but on a production line, the insulation's still over it, so you'd have no indication that there's anything wrong. Now the 64-strand wire with all but one strand connected, and we run a ground continuity test, it would pass it because it reads a continuous path. Whatever it is, even if it's 1 or 2 ohms, it still reads a path that says no problem. However, if you load that 10 amps or 20 amps of current down, that's going to fail. You're going to burn up that wire, and in all honesty, a product that has a default like that should fail. So it's something to keep in mind when you're considering which test to run. Now I want to show you guys a quick video. Now this one, you will tell immediately that I did it. It's not professionally done. Camera's a little shaky, so I apologize in advance. But what I did here is I set up a continuity and a ground bond test. So let me click on this. Hopefully this opens up okay. So what we have here is, you'll see I have continuity and a ground bond test. So I have a DC continuity test. I have a 3 ohm high limit. I have it set for 10 seconds, and I have no offset. I also am going to run a ground bond test right after this. So you'll see here I have it run 40 amps, a 6-volt drop measurement across the circuit, and a high limit of 150 milliohms, also a 10-second test. What are we testing here? And in a second, I'm going to show you, we're going to go over. Now in this plexiglass enclosure, I unbent a paper clip. That's all that is. It's a paper clip from high current to return. This simulates my one strand of wire. So what I'm going to do here is run both tests. So I just pushed the test button. I could hear the click in the background. Right now it's running the continuity test. We're about 6 seconds in, and you can see, no problem. We're going to pass this test. Now it's going to go right into the ground bond test. And as you can see, big difference between those two tests. That burned up pretty quick. That didn't even take 5 seconds before that thing fried out. So that, in my mind, is a perfect example of why the ground bond test is far more stringent than the continuity test, and why in most cases I believe even in production environments this one should be run instead. Obviously you might have products where you don't really have to worry too much about that, so hey, continuity test is more than fine. I'm not knocking the continuity test. A lot of our customers do continuity tests on the production line, and in most cases it's not an issue. But if you do a risk analysis on your product and you figure, hey, guess what guys, at this point in the production line we have a potential that we could nick our ground conductor, we might want to do a bond test instead. I've seen and been with customers who have gone through that risk analysis and decided they needed to do a bonding test, and as a result have caught defective products that they never would have caught with a continuity test. So both are good tests, both are necessary tests, but I wanted to point out the key differences between the two of them. That concludes our ground bond and our ground continuity our webinar today. I hope you guys got some really useful information out of this. If you'd like a copy of this presentation, let Jim know, jimk@asresearch.com, and check it out on our website. Also, feel free to follow us on YouTube and LinkedIn. We do have a post on LinkedIn. We always have threads going on up there talking about new products. And as you can see, every single video that I showed today is linked directly to our AR YouTube account. And you can also get most of those directly on our website as well. That being said, I really appreciate your guys' time today. We feel these webinars have been going very well this year, and we hope for your continued attendance to these webinars. We will be having one in June as well. Actually, I think every month for the rest of the year, save for December, because the holidays get a little fuzzy, a lot of people out, but we'll have our final one in November, and we'll be even doing a couple of these months. But again, thank you, and we're going to leave this open for Q&A for a few minutes before we shut out. Thanks again, everyone. Sure. Jim, could you hear Syed's question? I couldn't hear him through my headset, but I could hear him since he's sitting right next to me.
Actually, no, we did not hear Syed's question.
You didn't hear Syed? Okay. Basically what Syed just asked was he had a question coming up asking if people are performing both bonding and continuity tests in their testing environment. That's a really good question. I do know that there are customers of ours that do perform both, but not both on the production line. What they do is they'll perform their ground bonding testing for their prototyping phase, and then they're sampling on a sample basis. So maybe they'll pull a random product off the production line, take it to the lab, and bond test it. But as a routine test, they're doing the continuity testing. So in that sense, yes, they're doing both in-house, but through different aspects. Now, have I seen people who have done both on 100% production line? Actually, yes, I've seen that as well. We had a customer who was testing a very large product. They had multiple points, multiple chassis points on their DUT. And when I say large product, like this product was the size of almost a room. And they have all these different chassis points they needed to test. There were certain chassis points where they just needed to check continuity because there wasn't much of a concern for electrical shock on that part of the circuit, but they still wanted to make sure that these points were interconnected. But then there were the other points, the ones that were bonded, that they would do bonding tests. So I believe they would do something like 10 continuity tests, followed immediately by 10 ground bond tests, but keep in mind they were all on different circuits on the product. So to answer that aspect of the question, yes, I've seen it all run the gamut between running bonding and continuity. Well, I think we're good. Looks like Sad was able to handle most of those questions. Should you guys come up with questions, maybe something we weren't able to delve into, maybe something that would take a bit more time to discuss, please feel free to contact us, info@asresearch.com. We're always more than happy to talk about applications, questions you might have on this kind of stuff. Again, thanks for attending, and we will see you next month.